All right, we've got Andrew Graham. Hey, Andrew.
Hey, good to see you guys.
So tell us a little bit about yourself.
I'm an effects TD at Rising Sun Pictures. I've been using Houdini for around about 12 years. I've been doing CG for about 20. This is my 22nd year. I used to work at ILM, Sony, Weta Digital, Image Engine, to name a few. And that brings me to where I am today, which is I'm also the founder of Open Firehawk. So that's a side project that I've also been working on. And as a part of that, when I joined RSP, I was able to bring in some of those open source tools, and RSP have also been able to contribute back to those repositories as well.
Excellent. And what are you going to be talking about today?
So I'll be talking about how when you're using PDG, there's a Houdini package that can be used called Firehawk PDG Tools. And this doesn't have anything to do with cloud necessarily. It's just a way to provide a workflow that people might be commonly used to in visual effects studios. So it's meant to handle things like auto versioning, that each time you create a cook, that you have a meaningful way to increment a version of some asset on disk. And it provides hooks for studios or people that need it to be able to communicate with a database to make a request for a new asset version if that's needed. But you don't need to do that if you're an individual or you're a freelancer, and you don't need such things.
Cool. We're looking forward to it. Let's jump in.
PDG is able to produce a significant boost to our efficiency, and as an artist, I think also joy in being able to see pictures sooner. And I'm really glad to be sharing some of the work that I've been doing with PDG since it became generally available with Firehawk PDG Tools. So Firehawk PDG Tools has been contributed to significantly by Rising Sun Pictures while I've been there. It's also being used right now to run heavy simulations on a shot. Stormborn Studios also contributed to this project, where we used it on The Man in the High Castle, where it was used to run FEM-based bullet simulations to simulate the bending and tearing of metal. The main reason for the tool to exist is to provide an appropriate hook to be able to determine whether or not a version should be incremented, and providing a means to track when a version is incremented and persist that information within the scene. It also provides a means to handle very large numbers of outputs at any one particular point in a graph, so that we can determine many variations of assets in sequences and shots. If we've got one point in the graph that might represent 50 or 100 shots worth of output, how do we provide a meaningful way to track all that information and keep everything compact? Because normally that could produce a tremendous amount of data that would be very difficult to manage. When we're managing potentially that many different variations of output at a particular point in the graph, we also want to be able to logically only cook what we need and not always be locked into a framework where we're cooking way too much or way much more than we would really need. Another minor addition that it adds is the ability to create a time-stamped snapshot of the HIP file, so that that immutable version of the HIP file is utilized to reproduce any of our output. By also providing an appropriate hook for us to increment assets when they are cooked, that's also made available as a plugin that can be customized, so it's possible for you to interface with an asset database and request a new asset gets made, or perhaps you need to log an environment or other things like that when assets are created. We also want to make sure that when we cook, that we're able to auto version or increment a version. And one of the important reasons why it's open source is that it provides an easy to install Houdini package that can provide a common environment if we're trying to diagnose challenges or solve problems with side effect support as well. Does PDG reduce your resource usage? For a full iteration, the total amount of core hours that you might utilize would be the same. But that's not exactly the right question to ask, because prior to PDG's existence, I was in a scenario where a 36-hour simulation was able to be reduced to a 6-hour simulation just by having efficient per frame dependencies. You're also going to see a very improved usage profile for iterations that failed. Probably the most important way to look at this is how it affects emergent behavior at scale if this were used across an entire studio. Because previously, anything that doesn't have granular dependencies is going to create a bottleneck whenever that task finishes. So if you have to run a sim and you have to wait for the entire sim to finish before you can run some other parallel process, when that parallel process hits the farm, it actually represents a massive bottleneck before the next stage can occur. That bottleneck doesn't just affect one artist, it affects the entire team. And if it's a failure, it's even worse. So if you're able to implement per frame dependencies, all of that data is able to trickle through the farm. The total core hours are the same, but you're able to take scenarios where one artist who has some crazy deadline might take up a huge chunk of the farm, is instead taking up the same amount of resources, but within a slice that's been turned over in time sideways. And you could potentially have 10 artists doing the same thing, but they're all able to get their work done in parallel. You can force an artist to utilize less resources and still allow them to see some output. It also means that a partial failure or a partial iteration may be able to occur 10 times more throughout the day than otherwise would if we were running everything end to end. And that is the significant change, is what is the cost of a failure? Because most of what we do is a failure until we actually run a full iteration that succeeds, and it's something we either want to show in dailies or it's something we want to show to the client. Up until that point, those failed iterations represent a heavy chunk of the work that we do. And if we only have to run 10% of that to determine that it will be a failure, then we're using 10% of the resources for the cost of that iteration. So in terms of the emergent behavior that actually occurs when you apply this to how it affects your entire group and how it affects the consumption profile of all your resources, this is a totally different ballgame. This changes potentially how animation might even interact with effects. So animation might have something like a character that punches through a wall, or ground interaction. And if effects produce an asset which isn't just some effects output, but it's actually the procedural generation of that output that allows an animator to see how their character is interacting with a wall or how their character is influencing ground interaction, this can actually give an animator some informed process before they're even handing over their animation to effects to finalize the result. And so if we're thinking about orchestration of multiple shots or large numbers of assets across multiple shots, we really need to be thinking about not running things when they don't need to be run. So in a conventional old school wedging scenario, we often get locked into a world where if we have to run 100 wedges of something, we are just running those 100 wedges each evening. And if we're working throughout the day, we might only choose to run a few slices of those wedges at any one time, but we're also throwing away the context of those other 100 wedges that, for any other reason, should be there. So idempotency is an engineering concept that means if we were to have an operation that produces some state, and we were to run that operation the first time and that state's produced, if we run the operation a second time, there should be no change in state. And this goal, it's not trivial to achieve, but it is trivial to achieve some level of it that produces a heavily reduced resource usage pattern. If I have 100 shots that might be using a different simulation, but it's essentially the same procedural simulation, we have the means to efficiently run shots 1, 2, and 3 and have those updates propagate all throughout the graph. This is the test setup included with the package. So this takes us through a fairly common workflow where we might have destruction driving secondary simulation, and we might have 3 different objects or 3 different shots that are being simulated independently. We have this output prep node that essentially attaches the data that we might require for any submission in our pipeline, and most of that is actually contained entirely in the Firehawk PDG repository. The main goal that we have here is to essentially attach the data that we care about so that when these items are submitted, they have everything required to be able to run in our environment. In this case, we don't actually attach any version data at this point. We want everything that determines the version to be contained within the work item itself, because there's a whole bunch of logic when a work item generates and just before it's about to be scheduled that determines if the work item is going to cook or not. So one of the challenges with auto versioning is that if we place our versioning up here, which is something that I tried to do in the beginning, but I found that I was limiting myself by doing that. I found that I would basically have to determine all my logic up here to figure out if I would increment a version or not. And that meant that I was throwing away the ability of using things like cache handlers here, which are something I'll go into a little bit later. Essentially, all of the logic that determines if a work item is going to cook or not, it occurs at this point on the work item itself. And we are considering whether or not, when that work item gets evaluated, we're considering whether or not its output is already on disk. And if it's not, then it knows it has to cook. We also consider if a cook has occurred upstream. So if a fresh cook occurs upstream, then we know that a downstream work item also has to cook. And lastly, we have the cache handler. So in this instance, the cache handler, since it determines the output path, if that output path doesn't exist, I force a cook. If some other expressions aren't initialized yet, I also force a cook, because these expressions are essentially required to determine if we need to use logic to determine if a cook is needed in the future. So we have to initialize these expressions before we continue. In this setup, we're going to have 3 primary wedges, wedging 3 different objects that get fractured. And we're going to have secondary simulations, which we might have 5 wedges for each primary object wedge that we're going to distribute to be able to calculate the secondaries. The output prep node uses these primary attributes to determine the output path on disk. So the sequence, the shot, the element, the variant, which you might also call wedge, are essentially what determine this expression here. And that expression is the wedge ID. So the wedge ID will get constructed from this information, and that uniquely determines that particular output. There are other variables that might determine your output for an asset. So something like the extension or the asset type might change the actual output path. But in terms of variables that determine a unique output path for any particular output in our shot, this is the minimum number of variables that we use to define a unique output. Some of the advantages in operating this way are that it doesn't matter if we're talking about sequences, shots, or elements, or any variation in how we want to construct an element and a wedge name. We're always constructing a unique wedge ID, which is a string. And we still have wedge IDs available as numbers. Using wedge IDs as strings is much more useful at scale because you don't have problems with insertion as much. If you were to insert another wedge here, all of the numbers are going to change. But if you use a wedge ID as a string, like we do here, then inserting another shot will have no effect. It will have no negative impact. So if this output already exists on disk for each wedge, when that evaluates, nothing will happen. If there's no output that exists, then a cook will be forced. So if I clear the entries here and I were to cook this, because those paths were not able to evaluate for the expression that's defined here, no paths evaluated as having files on disk, a cook was forced. And so what's happening right now is we're generating new versions in the scheduler, which are then going to get picked up by these processes when they run. And also when the graph finishes, those versions also get picked up and they get propagated into the HIP file. So now that they're here, when we click on any of these work items, those paths evaluate to outputs that actually exist on disk. So because they exist on disk, if I were to repeat this operation, nothing will happen. If we want to force a cook, we can just remove an entry, or we can remove any number of entries. and we can dirty the node and we can cook again. And you see, because one of the entries already had an output there that was evaluated as being on disk, no cook occurred there, but the two work items that we removed, we were able to force a cook for. The other scenario where we currently force a cook is if there's no output expression, or if the expression here is invalid. That creates a problem because we have no way of actually knowing if we can evaluate an output path when we generate these work items. We're not really able to construct that information, and it means that the state of our HIP file isn't really consistent when we run it again the next time. So in that exception, we will also force a cook if the expression doesn't match the desired expression. That also catches scenarios where maybe you've changed your asset type or you've changed an output path. You want to catch those scenarios and you want to force a cook if you've suddenly changed the file extension. So you see here, after that cook finished, everything propagated, including the parameter expressions that we just removed. So we use custom cache handlers to be able to detect that the state is not in sync and it's not in the desired state that we want to be able to force that cook. Custom cache handlers are a really powerful way of determining your own logic for when a cook should occur. So you could use a custom cache handler on an output, and one scenario that I've considered that I'm kind of interested in is, well, what if that entire process was an HDA or just a single asset? We could generate a serial number based on the version and the contents of that asset, and we could also generate that serial number based on the asset's parameters itself. That unique serial number could be stored, and the next time we evaluate the custom cache handler, if that serial number is any different, we know that we need to trigger a cook. So custom cache handlers are a way of efficiently determining whether or not the data that we have on disk is out of sync with the desired state that we want a shot pipeline to be in. And so it doesn't really matter if we're talking about effects or if we're talking about the full end-to-end process of a shot pipe. Each department could be an asset within this pipeline, and those serial numbers can be utilized to determine if a cook should occur. I'm going to run the whole thing now, and I'm going to dirty this node with Shift D, and I'm going to force a cook by ensuring that those outputs don't exist. And since those cooks will occur, then the cooks will also propagate downstream. This node at the end here is also going to allow me to stream the output mplay session from disk into a live interactive session. So when I cook, we're eventually going to be able to see live mplay frames coming out to the desktop. This is a really handy workflow because this can actually keep the artist tapped into output even if that's on the farm. So this is one of the included nodes in the repository. It's a little bit of a hack. What we do is we actually load the generated output upstream as a background into another OpenGL session. So it's got a little bit of extra bulk in the operation, and there's a little bit of extra latency and resource usage associated with it, but the benefits that it brings are worth it. So what we're running here is the first stage we had our fracture. The second stage we had our fracture simulations. On the third stage, just before we generate our secondary simulations, which are located here, we also produce an SDF for our collisions. And we're getting per frame dependencies for each of the primary sims that relates to the 5 secondary sims that are also connected. So you can see frame 1 of our first simulation has a per frame dependency with the 5 secondary simulations that will follow. This allows us to maintain a per frame dependent relationship that could be across shots as well. There's no difference in this system between a shot or dealing with an asset. Everything is a wedge. So as the first frames for our secondary simulations start to finish, as soon as they're all complete, we can use a partition by frame node to write out a flipbook for us to have a QC process, so we can keep the artist tapped into the results that they're producing. It looks like all of our first frames are finished. So we should be able to now start up our flipbook process, which is going to write our frames to disk. And we're also going to get a live interactive end play session. And one thing I didn't go into is where I've customized this menu command where I have cook with pre-flight. We have a few operations that we run before we actually cook the graph to provide a few helpers with making the submission immutable. So if you look here, what's different to a standard submission is that we also take a timestamp of the HIP file. So we clone the HIP file and we use a timestamped copy of it. And we ensure that when things are scheduled, we're always trying to make sure that we're using this clone of the HIP file, which allows us to reproduce the result. But it also means that I can make changes in this current HIP file and not worry about that influencing the outputs that are currently running for this graph cook. So here are our per frame dependencies. It's a fairly simple scenario, but you can see we've got our objects 1, 2, and 3, and we've got, for each object, we've got 5 wedges that we're producing our particle simulations, and we have a per frame dependency all the way through the stream. There is a minor bug here that I should probably mention. It's a good example because although this isn't a critical bug, occasionally things show up in PDG, especially when you're going into edge case scenarios or you're figuring out some complicated set of relationships. You're bound to encounter some area that no one else has been in before. And that's another reason why I wanted to create this repository, because these scenarios, they happen, and you do want to have an environment that you can share with other people or with side effect support to be able to relay where the issues are coming from. And if you've built this entirely within a closed source pipeline, it's very difficult to produce cases that you can share with side effect support. One of the reasons for the existence of this package is to hopefully start to converge on some improved workflows around asset versioning. This is not perfect. It's not, completely production hardened. At the moment, this workflow is designed to function only when you're running a normal license of Houdini to execute your graph cooks. And I have a few ideas about how to change that. For example, this database is able to be flexible in its location. Depending on the nodes you're using, sometimes it may actually stamp that on something like a mantra node that exists in the top network. So it is possible for us to relocate that. It's kind of a minor point. Now that the graph has finished its cook, the next test is it idempotent? And so can I cook this location again and have essentially nothing occur? Because all those outputs are on disk, we're able to evaluate that they all actually exist and no cooks are required. This one's a little bit of an exception. It doesn't actually have output, it's reading input. So it doesn't really have any state. So it's a bit of an exception to whether or not it can run with idempotency. For that to be able to function, it would have to know that this data is on screen, and it would be able to say bail out or maybe bring it up into the foreground. There are certainly all sorts of scenarios that you're going to be able to create if you're not careful that prove we don't have complete idempotency. Like if I was to throw in some noise here and change something and I reevaluated this graph right now, we wouldn't be able to know, and we would actually be in a state of version drift where the HIP file that we're using right now isn't actually representative of the state of this graph. But that's why I was speaking to custom cache handlers before, and if something like that was actually something you wanted to go for in production, I would handle it by using something like an asset and serialize it and use that serial to be able to trigger a custom cache handler to determine if our output was out of sync. When that graph finishes its cook, we're able to switch between any of the wedges just by selecting any of those work items, and we can scrub through them. So in this scenario where we might just wedge the fracture, it's possible for us to do a simple file read with a channel reference to the literal output and have that data update. We can also then go down to our post sim transforms, where we're only writing out the transforms as points, and we can preview that data as well. And perhaps another scenario that's worth considering is when we want to collate all of our wedges in some locations all together. So at this point, we're reading all of the wedges that were written out here for this shot, and we're collecting them all in a threaded file read, which is essentially there. At this point, where we're doing this read, this is only really valid after we do a partition by frame node, which requires all of the wedges upstream to have completed any particular frame before the flipbook is able to preview that data. This is also a scenario where I found that using attributes wasn't able to really cut it, because this next process here, it needs to load all of that information, and it's not very simple to be able to maintain all of those outputs with all of their versions as just raw attributes. We need some way of persisting a key value store somewhere in the scene. So that key value store, when it gets scheduled, it's available to the work item itself. So when a new version gets requested, we have this key value store that we're always updating throughout the scheduler thread. So the scheduler thread always has this knowledge of all of the versions that are being incremented. Since the onSchedule thread, it's a sequential operation. So we're able to track all of the versions that are present at any point in time, and we can attach that to the work item itself. To be able to see some data, you have to collapse the batches. So in this case, the batch parent is like a container that contains all of those work items, and there's only one batch for this entire flipbook. There's an extra attribute that's attached to it, and if we want to inspect that, we have to open up a Python shell. I don't think it gets displayed here. I don't know why. I think that's because it's attached during onSchedule, but there is no version DB attribute here, and this is what I'm actually attaching. So in order for me to show you what's happening there, I'll get the current work item by doing this. But that's kind of a convenience method to get the actual current selected work item. Then we can say, let's look at the attrib names. Sorry, that's a method. And version DB will be in there. So if we say let's look at our work item, and we want to get our attribute named version DB, we can get the value. And so this is our JSON blob that essentially is a declaration of all of the things that we want to change when that HIP file loads. So in this case, it says whether or not we need to set a particular expression. It also tells us whether or not any versions need to get updated on any nodes that are not current. Basically anything in the state that needs to be changed. So this version DB is attached to work items, and it's able to be dynamically loaded when those work items cook. It's also then used to set things and change the state in the scene permanently. So unlike a normal parameter override, which we get built in with PDG, the purpose of this is to actually create some persistent change in state in the scene. And that declaration is something that updates the scene both in a work item that cooks, and it also updates the scene for the current user at any point we want to. If I were to say go and blow away a couple of wedges and I want to just reevaluate those, you'll see the missing wedges are evaluating right now. And as long as they're all scheduled, I can retrieve the submitted PDG versions that are in that submission, and this should be able to update all of the entries on our database here. So you can see that we were able to retrieve that same JSON blob, and we were able to pull in all of those versions in here. Another thing that we're doing is that while we're scheduling everything, we're also storing that declaration on disk as a sidecar file. And that isn't really meant to be read from while we're scheduling, because if you were to read and write at the same time, you might get issues. So we generally leave that thing alone. It's just there for recovery. So if the process was to get killed, or if this was running on the farm and a machine was to go down, or if there was to be a hang or a critical failure, the purpose of that file is so that when we reopen the HIP file, we're able to pull in all of that state that needs to be retrieved. I hope some of you out there find this useful. It's been a really interesting journey for me to be able to implement some of these more common workflows that we might be used to, and to also be able to add some extra abilities into PDG that I think makes it more useful in large scale scenarios and potentially managing large numbers of shots moving forward. I think it's going to be really cool when we're able to look at an entire shot from end to end and potentially use this as the means for being able to regenerate data over an entire sequence. It's possible, if you have really good tracking through things like cache handlers and serialization, for you to be able to use a graph that represents the entire output of a shot and hopefully make it easier to regenerate the output, provided those inputs still exist.